Assalamualaikum. In this session, we are going to learn about UV spectroscopy. UV spectroscopy involves the UV radiation and cause the electronic excitation. Before we understand in details, we should know that they have a difference energy between the molecular bonding, non-bonding and anti-bonding orbitals with the range 1 to 5 to 650 kJ per mole. In spectroscopy is called as a delta E, the difference energy between the lower energy to the higher energy, and this delta E must match with the energy comes from the electromagnetic radiation, and the energy that correspond to the electromagnetic radiation for this range of delta E fall in the ultraviolet region and visible region with the wavelength 200 to 400 nanometers for the ultraviolet and visible between 400 to 700 nanometers. When the sample had been inserted in the UV spectroscopy, what happened? The sample will be irradiated by the UV radiation and some energy had been absorbed, and this energy should be equal to the delta E for the particle to have electronic transition. And the remaining ultraviolet light will pass through the sample and it is observed. From this residual radiation, a spectrum is obtained, and this spectrum is called absorption spectrum. For any bond in a molecule, they have a mixture of atomic orbitals that called as a molecular orbitals. The bond that we understand inside the molecule always a sigma and pi. And they have one in the molecular orbital that we call as an anti-bonding orbital. There is sigma anti-bonding and pi anti-bond. And the lowest energy in the molecular orbital is sigma, and the highest one will be the anti-sigma orbital. Let's observe the electronic transition, the difference energy, which one is the highest and followed by the lowest one. The highest is the transition between the sigma to anti-sigma, followed by the N to anti-sigma, and the third one is the pi to anti-pi and the N to anti-pi. This is the sequence of electronic transition energy. What is N? N is actually the lone pair electron present in the NeHY heteroatom present in our molecule. Let's see what the group of molecule involved in the certain electronic transition. The most common for the transition between sigma to anti-sigma is the alkene group, because the alkene only have a saturated electron, saturated compounds, and they have only saturated electron inside. So they have no pi bond inside, and also there's no heteroatom. Means they only involve the sigma to anti-sigma. For the molecule that have a heteroatom, they have a transition between N to anti-sigma, which consider the molecule that have heteroatom oxygen, nitrogen, sulfur and halogen. They will involve this electronic transition. Next, for the unsaturated compounds like alkene, alkyne, they will have a pi bond, and this transition we will see the transition between pi to anti-pi. And when it comes to the unsaturated compounds with the presence of heteroatoms or carbonyl, it will have a transition between N to anti-pi. This is the lowest difference of energy, but what happened to the wavelength, it will show the higher wavelength. As we know, from the formula of E equal to hc over lambda, means energy is inversely proportional to the lambda value, wavelength. Means when the higher energy here, we have a shorter wavelength, lower energy we have a longer wavelength. Let's see the example in details. Between each transition, the first one is the sigma to anti-sigma. This type of transition, as I mentioned just now, is the largest energy difference. Means when the largest energy difference, the wavelength will be the lower. So you can see the methane only absorb 125 nanometer, ethane 135, because this is the highest energy difference, the highest delta E, so the shorter the wavelength. We followed the formula E equal to Hc over lambda. Means energy higher, lambda will be lower. This alkane possess sigma bond. As we know, alkane only have a sigma bond. They have no pi bond because they are all saturated electron. So means they only have one transition, which is sigma to anti-sigma transition. This is the higher energy, so that's why they have a shorter UV wavelength. For the second transition is N to anti-sigma. N to anti-sigma means in the molecule have a heteroatom. Heteroatom like oxygen, halogen, nitrogen, they have a lone pair. So they have involved for example, the molecule in alcohols, the saturated CCC, and then followed by the OH, and this molecule alcohol will have two type of transition, which is sigma to anti-sigma and also N to anti-sigma. So because of the arrangement of the difference of energy, N to anti-sigma is the second higher, means they have more longer compared to the sigma to anti-sigma wavelength. So we can see the absorb is 167 nanometer. Just now, if we alkyl group 13125 something nanometer. That's the difference. Because the energy also difference, the wavelength also will be difference. And this is the example for the N to anti-sigma transition with the presence of OH and with the presence of sulfur. Then we have consist two type of transition for this type of compound. Just now I mentioned sigma to anti-sigma and also N to anti-sigma. That's why in the UV-VIS they have 2 lambda max. Why? Because of this different electronic transition. Next transition is the pi to anti-pi. This transition occurs in unsaturated molecule. Mostly for the double bond, triple bond, and aromatic compound, we involve this electronic transition, pi to anti-pi bond. For example, alkyne carbonyl compound, cyanide azo compounds. This is type of compound that involve for the pi to anti-pi transition. So as we can see, the absorption or lambda max will be more longer. Why? Because this is a shorter energy. It is difference energy is not as high as sigma to anti-sigma and N to anti-sigma. We can see the difference is quite smaller compared to the sigma to anti-sigma. That's why the absorption is more comes to the longer wavelength compared to these two electronic transition. For alkyne, we can observe the pi to anti-pi in between 175 to 170, and it also sometimes it have also inside the molecule it have transition between sigma to anti-sigma. That's why they have a different wavelength for the absorption for the lambda max, because the peak always not only one peak, it will have 2 or 3 lambda max. Next, the last one is the N to anti-pi. N to anti-pi, when the unsaturated compound have a heteroatom like oxygen, nitrogen, halogen, this electronic transition is the lowest energy, and this will have the higher wavelength number. If you can see this one, for example, saturated aldehyde have a heteroatom, which is C double bond O, and itself has C double bond, means they have a transition between N to anti-pi and pi to anti-pi. So they have a two lambda max, which is the lowest energy, the higher wavelength, the longer wavelength 290. This represent for the N to anti-pi, and this represent for the pi to anti-pi. That's for the four electronic transition that we should understand, and what's the organic compounds groups belongs to each electronic transition. And this is the example for the carbonyl group. For example, aldehyde, carboxylic acid, ketone, ester. All these consist of this electronic transition, which is N to anti-pi and also pi to anti-pi. That's for electronic transition. Now we go for the principle of absorption spectroscopy, which is Beer's law. Beer's law always say that the absorption of the UV light is directly proportional to the concentration of the sample. This is the formula for the Beer's law, and the principle that we should understand, the absorption is directly proportional to the concentration. This is the selection rules. When the sample when the electron had been arranged in the molecule, the electron always in the opposite spin state, mean above and below. This is the Pauli rules. We had learned it previously in all inorganic and in our matriculation about the Pauli arrangement of the electronic must be up and must be down. Cannot be both up or both down. This is the Pauli rules of the arrangement of electron in the orbital. And the spin selection rules, they also must be in a different spin, means must be up and must be down. This type of, there's no transition will be allowed. And the bonds, the band structure, the band that we have, although they have a different electronic transition, the band that have been read always overlapping band, and we see the spectrum in form of overlapping band. And this is the instrumentation for the UV. As we can see, the small inside our instrument, they have a UV source light, and they have a splitter for the light with the region, the function of the to split the light, and the monochrome is to split the light. And our sample will absorb the light, and the light that have been absorbed will be released, and this release we call as a absorption spectrum. And the two source of light that we use in UV is deuterium lamp and tungsten lamp. And the detector always measure the light that have been transmitted out. And how to sample handling, we have to put our sample in the cuvette with the transparency to the 200 to 700 nanometer range of light. This is common cuvette, whether it is plastic or glass cuvette. The clear must be passed through by the light. We should correctly insert our sample in the UV spectroscopy. Next, when we use a solvent, they have a solvent cutoff. That's why they have a region that we set between before we run our sample, because we want the cutoff common solvent wavelength. Normally we set between 200 to above, because we want to cut off the acetonitrile and water. If we use methanol, we have to cut off. We set our instrument between 210 and above. Why we need to know the cut off common solvent? Because we don't want the absorption from the solvent to be interrupt our data from the sample. So how to sample handling? Must use the correct solvent, and the solvent cannot have a hydrogen bond with the sample. And this is the example of the spectrum, absorption spectrum that we can see. This is the lambda max absorption of the light absorption, and this is the light region, nanometers, the wavelength. This is the peak that we call as a lambda max. Why this compound have a 4 lambda max? Because they have a 4 different electronic transition inside this molecule. That's why they have 4. Because we learned they have 4 electronic transition just now, so that's why they have a different lambda max. For each molecule, they will have more than one of the lambda max. So practical application for UV, it can be used to determine the functional group. It can be used to assay the irradiation wavelength. It can be used to determine extent conjugation system, and we can know the clue of the unknown compounds, and we can identify the polynuclear hydrocarbons. That's all for today. Thank you.